Okay, good morning, everybody. Hello, can you hear me? Okay, before I start, just to make sure, can you all see the screen, the PowerPoint presentation? Yes? No? Okay, good. This is just going to be the second lecture of section 6.5 and 6.6. Actually, we don't need more than 2 lectures to cover those 2 sections. Before I start directly into the examples, because once we solve the example, then you will be ready for the tutorial sheet. So today I shall just elaborate on the example and then go to the tutorial sheet. Anybody has any problem on the supporting material that I uploaded? You need by the end of lecture, you need to be able to determine the phase. Once I give you 2 properties, then the phase can be or should be determined. Anyone had a difficulty in that? Was it clear? Did you try? Yeah? Is it clear? I can't proceed if it is not. Clear? Okay. Okay, so apparently it was clear for the student, then it's fine. So here is an example. Now, how we are going to use chapter 6 then in solving problems? It's mainly we are going to use it through defining the state and finding out or getting the properties from the thermodynamic tables, which are table F1 to F4. Here I have an example. Let me just clarify how can we solve a similar example here. Okay, what we have here, we have superheated steam that originally at T1 and P1. So the idea here is that I have steam that gets into a nozzle. So a nozzle is normally represented by this symbol. So this is the symbol of nozzle. I have the inlet of nozzle and I have the outlet of nozzle. And according to the given information, the inlet has a temperature T1 and P1, and the outlet, it expands so that the pressure becomes P2. So upon expansion, you are expecting P2 to be less than P1. Now, what it says here, it says that the process is reversible asentropic. And when it says that it is reversible asentropic, it means it is, reversible adiabatic, it means it's asentropic. So I know that delta S here is equal to 0. Okay, Q is equal to 0. And delta is equal to 0 because it's reversible adiabatic. Now, what we have in this equation, we have been given 2 scenarios, A and B. Actually, they are both same, except that the first one is an SI system, the other one is an English system. Now, just a quick elaboration on one of them, part A, let's say. To solve, well, first of all, we need to know what they need. They need from us, number 1, to determine the state of the steam at the exit. And because it's at the exit, as you all know, we have to define, we need to have at least 2 properties to fully define the system according to Gibbs phase rule. Now, with the initial temperature and pressure, okay, you have the pressure is given as 1000, the temperature is given as 523.15. This is the initial temperature, which is 250 degrees C. Okay, now the point is, at point 2, you only have 1 property. You cannot solve if you have 1 property, or in other words, you cannot define the state if you have only 1 property at the outlet. But the idea here is this: since you have been given that delta S is equal to 0, this is going to be the relationship between the inlet and the outlet. If delta S is equal to 0, then once from the thermodynamic table, once I put S1, then I would just say here S2 is equal to S1. And in this case, I would have 2 properties, and from those 2 properties, I can solve the problem. So this is how you solve the question. Okay, unfortunately, I cannot wait for you to go to the thermodynamic tables and check, but I will just explain the idea, and then take your time, revise the question, and see if you can get the same information from the thermodynamic tables or not. So what I did here, at the initial condition T1 and P1, just 1 second. The initial condition at T1 and P1, and here you have to ask yourself which table I have to use. It was clearly written it is superheated. it means you are going to use table F2. And from table F2, the first column given in table F2, it was based on the pressure. So you will get this pressure, and then you will go horizontally, find out at 250 degrees C how much is the entropy. And actually, you will find that 200, it really depends on which table you are, well, here, when you go to table F2, you will find that 250, it is in between 240 and 260. In other words, you will need to do interpolation. In this question in particular, because 250 is just exactly in the middle between 240 and 260, then maybe no need to do interpolation, but get the average of the properties S at 240 and S at 260 and just average them, because it's exactly in the middle. Otherwise, you would have to do interpolation. So what I did here, I got S1, which I need. And because S1 is equal to S2, because it's reversible asymptotic process, then at the exit, where the pressure P2 is 200 kilopascal, and at S2, we have to go and define what is the state. S2 is 6.9252. Okay? All right? So here is the idea. Now, you notice here that I did not only find S1, I found H1 for a reason. I will tell you the reason later on. Now, what I have here, at those pressure P2 and S2, what I did, I went to the thermodynamic table again, and at this pressure, 200 kilopascal, now since it's pressure-based, then that's why I went to F2 again, table F2. And when you go to table F2, at that pressure, so you have the pressures written, you go to 200 kilopascal and then go horizontally, try to find out what is the state. If you remember, I already mentioned that in table F2, the first two columns are those for saturated condition. You will notice that at this 200 kilopascal, your S that you have here is actually in between. And what in between means, it's in between S of the liquid and S of the vapor, the saturated liquid property and the saturated vapor property, which is the entropy here in this case. So if that is the case, if S is in between, then it is what? It is saturated mixture. And because it is saturated mixture, I had to find the what? The quality. Remember, the quality is very important for saturated mixture. If you don't have the quality of saturated mixture, you cannot find any properties at the outlet. Why is this? I'll just repeat what I said in last lecture. In the PV diagram, saturated mixture simply means I have a region. What do I mean by a region? It's a full region here, that region. It's all saturated mixture, but it really depends on how much is the quality. If the quality is 0.9, then I will be able to define exactly the state where is it. If it is 0.1, so knowing the quality will exactly tell me where is the point. And because of that, what I did here, I got the quality value. Reason is the quality will tell me exactly where is the point, and in this case I can find any other properties. According to the question, all they ask for is just to define the state of the outlet, and that's enough by saying it's saturated mixture. But I just modify the question so it becomes a practice for you. What if I ask you, for example, to find the enthalpy at the outlet? To find the enthalpy at the outlet, again you will go here from the properties, from the table F2 at 200 kilopascal, you will get H of liquid. Okay, you will get H of liquid. Okay, sorry for that. Okay, so what you will do here, you will get the H value of liquid, you will get H liquid and H vapor, you will get H liquid here, you will get H vapor here, then you will substitute in the equation. What is that equation? The H that you want to calculate is equal to 1 minus X vapor into H liquid. In other words, it's X liquid, H liquid, plus X vapor, H vapor. And upon substituting, you'll be able to find H2. That is, if they ask for H2. Then what if they ask for applying the first law of thermodynamics? For example, here, I'll just skip part B because it's exactly the same procedures. But I want to show you further calculation. If they ask you, for example, to find the velocity at the outlet, as an example, okay, if they ask for such thing, then you will apply the first law of thermodynamics, and with the nozzle, you all, according to the question, there is no heat transfer, and there is no work with the nozzle normally. So delta H plus change in kinetic energy plus change in potential energy is equal to 0, and change in change in the potential energy is 0 in this case, you will just substitute and find the velocity. Here, if they ask for finding the velocity, okay, and you can see here they only put the velocity at the outlet. They were just considering that the inlet velocity is much smaller than the velocity at the outlet, and that's why it has been cancelled out. But this is how you are going to get questions in this chapter. By using the thermodynamic table, you will be able to just substitute and get the values of whatever they need. So these are kind of a question that you will solve. Now, I'm done with chapter 6, but I want to clarify something important. You cannot solve all the problems in chapter 6 because we are only covering 2 sections, which is 6.5 and 6.6. So those are the recommended questions which I feel useful and related to both sections. And what I will do now, I will just go through those problems just to make sure that you are getting the idea. And please practice them yourself, because especially with chapter 6, without practicing the thermodynamic tables yourself, I think you will just get difficulties in defining the phase and understanding how to solve problems. So what I have for you here then is tutorial 10, which is the problems that I just put as suggested problems. So in the coming 20 minutes, I need to discuss those with you. Can you just tell me if you can see the tutorial sheet? Is it clear? You can see it? Yes? Please? Hello? Okay, good. So let's see how can we discuss this. What I have here, we have, according to the question, we have wet steam. Now, we have to be careful here. The word wet steam, wet means what? The word wet simply means that it is saturated mixture. So this is the first thing you have to know. So, okay, so I have here wet steam. Okay, I hope I won't face similar problem to the problem I got last time. I think I'm having the same problem. Okay, I think it's just not allowing me to use the ink for some reason. Let me see. Okay, no, it's not working. Bismillah. All right. So what I will do, maybe it's better that I discuss with you each question, and then when you start solving yourself, maybe you have an idea. Here, it says it is wet steam. So whenever it is wet steam, it simply means that it is saturated mixture. Wet steam means I have both liquid and okay, so what I will do, I guess, just not allowing me to do anything. Okay, I'm sorry for that. It seems that I have a technical issue here, which did not happen before. I hope it works now. No, it doesn't. Yeah, it seems whenever I write, it just gets, okay, I don't care about whether it's deleted or not, but keep with me, following with me. Here, I have wet steam, and when it says wet steam, it simply means, Okay, which steam? It simply means that I have saturated mixture. So according to the question here, I have been given the temperature, I have been given the density. Now, what they ask for X, and you know that X is equality. So what I need to do here, I need to find this equality, provided that HS were also unknown. So I need to find HS and I need to find the equality. طبعا I know that it is saturated steam. So in other words, it is saturated, with steam means saturated mixture. Now, as we agreed, we need to know two properties to fully define the system. Now, according to what we have here, we have the following. The temperature is given. Okay, the temperature is given, and that temperature was 230. So what you are going to do is this. You need to go to the table, which is appendix. Okay, I'm sorry. It just seems like okay. Please accept the oral discussion, and then you follow up when you start solving. So here. The temperature is given. So if it is saturated mixture, then table F1 will be enough. So you go to temperature 230 degrees, say, and that's what is given here is the density. I don't have density in the thermodynamic tables, but what is the closest property to density? The closest property to density is the specific volume. So 1 over this density will give the specific volume. In other words, all you have to do is by knowing this temperature, which is 230, you will go to the thermodynamic tables and be close to the volume, specific volume property. الحين at 230 degrees C, you will find in the thermodynamic table that you have V liquid, V vapor, but you don't have the actual V. Actually, where is the actual V? It is the inverse of 0.025. Why? It is the inverse of 0.025 because this is the actual density of this stream. And the actual density of the stream, by inversing it, I will get the actual specific volume. So what we have here is this. We have the actual specific volume. From the thermodynamic tables, I have the V liquid and V vapor. And in this case, I can apply the saturated mixture equation. What is this? Which says the property M is equal to X into M liquid plus X liquid M liquid plus X vapor M vapor. So the quality X here, whenever they write X here, this equality simply means it is mass fraction of vapor. But now when I want to substitute, it's going to be okay. Let me just go to here. Okay, I'm just going to go to the slides again, the PowerPoint slide. So when I say M liquid, when I say the property M is equal to M liquid, X liquid, plus M vapor, X vapor. This simply means that to find the quality X, it's 1 minus X, M liquid, plus X into M vapor, because X here simply means X vapor. So all I did is just replacing X liquid by 1 minus X. This is what I did. In the question, that M here is the specific volume. So the specific volume is 1 minus X into vapor of liquid plus X into specific volume of vapor. So this is how it is. Or I told you previously, that you can apply the same relationship but in a different format. What is that format? It says that if you want to find any property, it's going to be equal to the property in liquid phase plus the quality into the property LV. And that LV, it's the difference between V vapor minus V liquid. This is how we mentioned it last time. So whether you are going to use this equation or that equation, both of them will give the same answer. Actually, the second equation came from the equation before. So what we have to do then in the thermodynamic table, we have to go and get M liquid. M liquid means the specific volume of liquid. Where is this? At the given temperature. The given temperature, it was 250 degrees C. So from table F1, you will go to 250 degrees C and find the saturated liquid property of specific volume, the saturated properties of vapor, which is the specific volume of vapor. Then it's just direct substitution. That one, keep in mind, it is 1 over rho, which is the given in the question. In this case, the only unknown is going to be the quality, and here you can just solve and get the quality as they needed. Remember, once the quality has been obtained, then anything they ask for, you can solve. Why is this? Or you can calculate. Why is this? Because H can be again found from H liquid plus X HLV. Same thing if they ask for U, for example, internal energy. It is U liquid plus X ULV. So in other words, once you calculate the quality from here, خلاص, anything else can be calculated. So this is the idea of this question, which is 6.25. I'm sorry, guys, I'm just not feeling happy with the layout of or the performance of today's presentation because of the technical issues. But is 6.25 clear? I know, Ali, I can use OneNote like last time, but now I don't want to open it and then copy and paste. So I'll just keep using the PowerPoint presentation, copy from the Word to PowerPoint presentation. So are you okay with 6.25? Do I need to re-explain it? If okay, I'll just proceed the same way. I'll just copy the question to PowerPoint and then solve. Okay, guys? Okay, thank you. I highly appreciate your understanding. All right, so back to the question. I'm done with the first one, so let's go to 6.25. It just sometimes doesn't even, okay, so I'll just copy this and go to the PowerPoint presentation. And I prefer even to get a new screen. Okay, so let's see what we have here. Okay, so let's see what you have this question. Here, I have steam. The steam, it is at 2,100 kilopascal, so the pressure is given as P1. The temperature is given here as T1. It expands at constant enthalpy. When they say constant enthalpy, you mean delta H is equal to 0. And this is equivalent to what we have with the throttling process. Remember, we said already in throttling process that delta H is going to be equal to 0 if it is, if no heat transfer, no work is done, which is normally the case. But with the throttling process, normally we get reduction in pressure. So if we consider this as our throttling process, okay, the throttling process, we do have like throttling system, like valve or whatever. I will explain that in detail in chapter 7. But according to the given information, T1 was given, P1 was given, and P2 is also given as 125 kilopascal. And I hope you can clearly see that P2 is much smaller than P1 because this is mainly the duty of the throttling process. The pressure is reduced significantly. So what they ask for here, they ask for the temperature. What is the temperature of the steam in the final state? So this is the first requirement, the temperature in the final state. Second requirement is the entropy change, delta S. Okay. Then they were asking, can you repeat the same thing? In other words, finding the final temperature again and the entropy change again if it is ideal gas. So this is not chapter 6, this is chapter 5. They were asking, considering ideal gas behavior. Now remember, the thermodynamic tables we are using are actual data. They are not based on the assumption of ideal gas behavior. They are actual data. When they ask for ideal gas, I'll start with the second part because it's related to chapter 5 and we need to finish off that. With the final temperature, if delta H is equal to 0 and it is ideal gas, I'll just remind you with the condition we said, if it is ideal gas and delta H is equal to 0, then H is a function of T only. And in this case, T1 is going to be equal to T2. As simple as this, which is 260 degrees C. And to find delta S for ideal gas, it is simply Cp ln T2 over T1 minus R ln P2 over P1. Again, as simple as this. Temperature here is same, then I will end up with only minus R ln P2 over P1. So all we have to do then is just to substitute and get the entropy value. So that is if it is what? If it is ideal gas. But now, with the actual data, which is chapter 6, the first part, this is part 2. What I did is just part 2. Okay, using chapter 6, I'm going to solve part 1. Now, again, you have to ask yourself, how can we use the thermodynamic table? But in the question, they were asking for the temperature at the outlet. And again, I'm saying that because I have only P2 at the outlet, one property, I won't be able to define the state at the outlet because it's only one property. Then we have to ask ourselves, what is the common property between the two. It's H, because they said delta H is equal to 0. In other words, H1 is equal to H2. So the procedures are going to be as follows. At C1 and P1, you have to go to any table. Let's say table F. I would go to table F2 because I do have the pressure there, and I know that the pressure 2,100 is there. So you can use table F1 and check. Actually, you will find, from my experience, you will find that the temperature T1 is you will find that the temperature T1 is greater than Tsat. And according to last lecture, if T is greater than Tsat, then it is superheated. Okay, so with superheated, using table F2, go and have a look horizontally until you get the value of H. So you will find H1 from table F2. So this is the step number 1. Then step number 2, you will say H1 is equal to H2. And in this case, at a pressure P2 and H2, you have to fully define the system. And here again, you have to go and figure out what is the property. Now, according to this question, which is at P2 and H2, you will again find that it's also superheated. Why it is superheated? Because you will find that your H, the property H2, is greater than H vapor. And if it's greater than H vapor from the table, then it is superheated. Okay, so what is the next step? They were asking for the temperature. Of course, having two properties, H2 and P2 and H2, you will just go horizontally in the table until you reach to the intersection where at this P2 and H2, at this P2 horizontally, and you will get H2 somewhere. Then you have to go vertically, find how much is the corresponding temperature, and you will get the reading of the temperature from the x-axis. I'm sorry, I really need you to practice yourself. Go and check, can you read and get the value or not? Okay, and this is basically the idea of how to solve it. And I think, according to what is given here, you will find that the final temperature is 224.8. Probably you will need to do interpolation degrees. Okay, probably you will need to do interpolation. So I will leave that to you. Make sure that you can solve to get the correct values from the thermodynamic tables. Now, last thing I want to say on this question, that keep in mind here, you can find temperature and also you can find the entropy, because at this H2, if you cannot find the exact H2, you can find it using interpolation, but you will also find S2 at the same location. Okay, and you will get it by interpolation as well, and it's going to be 7.8316. All right, I don't want to put more new here, but just to remind you, the units of the entropy is joule per gram Kelvin or kilojoule per kilogram Kelvin, according to what's written at the top of table F1. But when you find from ideal gas, here the unit is going to be joule per mole Kelvin. So you cannot compare the two unless you convert using the molecular weight of the steam, which is 18. You can convert this to joule per gram Kelvin, and you can compare the two values. So that is just an approach if you want to compare between the two values. Okay, so this is question 628. Let me see here with 6:30. I know I have only 2 minutes. Maybe I would have to stop. What I will do, I will leave the remaining problems for you. Beginning of next lecture, which is Thursday, today afternoon. We will continue in this case, and today afternoon we'll just continue discussing those problems, if you don't mind. All right, so I'll have to stop now as an end for this morning session.